Assalamualaikum warahmatullahi wabarakatuh. To Miss Anisha Finas binti Mat Marzuki. Today we're going to present about experiment 6, which is high performance liquid chromatography. This is our group members. At the top is Hanan Shafi bin Azhar. At the right side is me, Muhammad Khairi Danish bin Hamzam. At the left side is Muhammad Danish bin Abdul Halim. At the bottom, Muhammad Akmal Zarfan bin Nur Hisham.
So now let's move to the introduction. High-performance liquid chromatography (HPLC) is a powerful analytical technique for separating, identifying, and measuring components in mixtures. Analytes are first dissolved in a solvent, which is then forced through a column under high pressure to complete the process. The versatility of HPLC is impressive, since it can effectively separate a variety of chemical mixtures, including thermally labile compounds, manufactured or natural polymers, and non-volatile and thermally unstable molecules, including organic, inorganic, and biological components. HPLC has several advantages, including high sensitivity with different detectors, reusable columns, and sample recovery, utilizing fraction collectors. It is particularly effective for analyzing ionic species, big molecules, and substances such as lipids, amino acids, toxins, vitamins, carbohydrates, pesticides, and organic acids. In analytical research, HPLC is crucial for both small-scale analysis and large-scale purification of pure chemicals.
So now we look on the objective. First, to determine the retention time of a standard solution, which is a caffeine. Next, to identify the caffeine peak in a soft drink sample. And the last one, to determine the amount of a caffeine in a soft drink sample using the response factor method. So here is the fully block label diagram of a high-performance liquid chromatography. It is starts with the solvent reservoir, following by the pump, injector, column, and the last one is the detector. So here is the name and the function of each component. For the first is a solvent reservoir. The common type of reservoir is a glass bottle with special cap, Teflon tubing and filter to connect the pump inlet and to the purged gas of helium used to remove gas by process of degasser. Degasser to ensure reliable chromatographic performance. Dissolved gases and dust must be removed from the liquid. Dissolved gases can cause irreproducible flow rates and a band spreading, while bubbles and dust can interfere with the detector performance. Additionally, particles in the liquid can damage the pumping and injection system or clog the column, leading to the system of malfunction. Second is a pump, a function to force the mobile phase to flow through the packing of system. The pump is essential for maintaining stable flow and preventing pulsation in the chromatography system. Common type of pump used include reciprocating pumps, displacement pump, and the last one is a pneumatic pumps. Third is injection that are function to delivering the sample into the chromatography system at a precise volume and pressure, ensuring reliable and reproducible chromatography separation. There are three main types, which is shrink injection, sampling loop, and auto-samplers. Shrink injection, the simplest method, uses a micro-shrink to manually inject the sample through a self-sealing septum with turning pressure up to 1500 psi. Sampling loop, the most widely used method, hold a fixed sample volume and a low injection under high pressure up to 7000 psi. Auto-samplers automate the process, efficiently handling multiple samples stored in vials, ensuring reproducibility and a high throughput analysis. Next is the column. It is separate to analytical column and guard column. Analytical column are separate compounds based on their interaction with the stationary phase with precise dimension for effective separation. The guard column protects the analytical column by preventing contamination, clogging, and deactivation, extending its lifespan and reducing band broadening. The last one is the detector. It is function to identify and measure the presence of compound as they pass through the system, providing the data for analysis. Detector can sense change in the properties like UV absorbance, refractive index, conductivity, or fluorescence, depend on the sample being analyzed.
Hi, my name is Hanan. Right now I will be presenting the results of our high-performance liquid chromatography analysis focusing on caffeine detection in standard caffeine, Coke, and Levita samples. The result indicate the following retention time and peak areas for each compound. For standard caffeine, the retention time was 2.481 minutes with a peak area of 6,249,48779. Similarly, for Coke, the retention time matched the standard at 2.481 minutes with a slightly higher peak area of 7,001, suggesting a higher caffeine content compared to the standard. Meanwhile, the Levita samples showed a retention time of 2.019 minutes with a peak area of 3.48617 times 10 to the power 4. This distinct retention time implies that the Levita sample contains a different compound or possibly a derivative of caffeine, which I stated earlier. So in this discussion, we will analyze the high-performance liquid chromatography result for the standard caffeine sample. The key parameters include retention time, peak area, peak height, and width. The retention time for the standard caffeine sample was recorded at 2.482 minutes, indicating successful detection and quantification of caffeine. A single prominent peak was observed at this retention time, confirming proper column separation without any contaminants or overlapping peaks. The peak area was measured at 6,249 with a peak height of 1,196 and a width of 0.0730 minutes. These values highlight the sharpness and resolution of the peak, ensuring the reliability of the detection process. The retention time consistency and sharp peak appearance demonstrate that the column used was well suited for caffeine analysis. Achieving effective separation, the absence of addition peak further supports the purity of the sample and the accuracy of the method. In summary, the Hplc analysis of the standard caffeine sample confirms accurate detection with a retention time of 2.482 minutes. This result provides a solid baseline for comparing caffeine presence in other samples. Next, let's discuss the caffeine analysis in the Cook sample based on the chromatographic data. The chromatogram reveals the caffeine content and other components present in the beverage. Let's focus on the key results. The retention time for the caffeine is 2.481 minutes, which corresponds to the largest peak in the chromatogram. The peak area is 7,001, indicating the significant quantity of caffeine in the sample. The peak height is 1,465, showing its prominence in the analysis. The peak width is 0.0677 minutes, confirming a sharp and well-defined peak. The large peak at 2.481 minutes is attributed to caffeine, which dominates the chromatogram. Smaller peaks represent other components in the Cook sample. This could be preservative, flavoring agents, or other substances used in the beverage formulation. This analysis highlights that caffeine is a major component in Cook, accounting for the majority of the chromatographic area. Other substances, although present, contribute smaller peaks. So let's discuss the caffeine analysis in the Levita sample, focusing on its chromatographic data. The chromatogram showcases the caffeine content in Levita and highlights the efficiency of the analysis process. The retention time for caffeine is 2.019 minutes, corresponding to the largest peak in the chromatogram. The peak area is 3.48617 times 10 to the power 4, indicating a significant quantity of caffeine in the sample. The peak height is 2,656, confirming its prominence in the analysis. The peak width is 0.1596 minutes, which suggests a sharp, well-defined peak. The sharpness of the peak indicates good column performance and proper separation of the compounds in Levita. The retention time for the peaks are consistent with well-separated components, ensuring accuracy in identifying caffeine. Smaller peaks are observed, representing other compounds in Levita, which could include additive or flavoring agents. This chromatographic analysis highlights caffeine as a major component in Levita, with efficient separation and identification of its compound. The result confirms the quality of the analytical method used.
Calculation for data number 1, standard caffeine. Formula for retention factor is peak area of caffeine standard over concentration of caffeine standard. Peak area standard of caffeine is equal to 6249.487 milliabsorbent divided by given caffeine concentration is 0.1. The answer is 02494.87 milliabsorbent mg per mil. The baseline was stable with minimal noise, allowing accurate peak detection and measurement. For the next data is caffeine in Cook. From previous equation, retention factor for caffeine is 6249.8779 milliabsorbents. From the result, retention time for caffeine in Cook is 2.481 and the peak is 0.7001.123 by using formula. Concentration of caffeine is equal to peak area caffeine in sample over retention factor, which is 7001.123 over 62494.87. The concentration of caffeine in Coke is equals to 0.112 mg per mil, which is equal to 112 ppm. For caffeine in Levita, where retention factor for standard caffeine is 62494.8779 milliabsorbents. For concentration, we are using the formula. Concentration of caffeine in Levita is equals to peak area caffeine in sample over retention factor, which is 1.11511 decimal 10 power of 4 over 62494.8779. The concentration is equal to 0.178 mg per mil, which is equal to 178 ppm.
So now we will move to the conclusion. The Hplc analysis met the study's objectives by calculating caffeine retention durations, finding peaks in soft drink samples, and quantifying caffeine concentrations using the response factor approach. The water, Co and Levita samples all had retention durations of 2.482, 2.481 and 2.019 minutes respectively. Clear chromatogram peaks verify caffeine's existence, whereas secondary peaks suggested other components. While Hplc proved effective, different techniques such as GCMS for structural details, UV-vis spectroscopy for rapid screening, and capillary electrophoresis for high sensitivity could supplement caffeine analysis depending on the demands and resources.